Today I am going to talk about operating systems, issues with operating systems, what operating system description notion is, and if time permits, I will start introducing programming languages, and I will start introducing C programming language. I will be starting on that topic. So when focusing on these issues, we will be discussing about history of operating systems, architecture of operating systems, how we coordinate activities of a computer, process concept, what are the processes, process or tasks, and issues like security, operating system security is important. So for this purpose, I would like to have you watched the following video. It is time-sharing video by Fernando Corbato in 1960s. It explains a lot of fundamental principles. It gives good idea about how computing was in those years. Also, it explains basic structure of today's operating systems. It's a nice video. So, what are the operating systems? I tried to list them on the right side. Unix, Xenix, NOS, Linux, Windows, Mac, Multics, OS2, VMS, MacOS, iOS, Android, CP/M, DOS, etc. So there are other operating systems. Those operating systems, Symbian for Nokia in the old days. Those operating systems generally are responsible of a lot of different duties, functions. Those functions are coordinating the whole operation of the computer, storing and retrieving files, storing and retrieving data, processing that data, so coordinating of the execution of the data, scheduling programs for execution. Which program is going to be executed first? Which program is going to be executed after that? How long it's going to be executed? In which part of the memory it will be executed? Those kind of issues are handled by operating systems. Yeah. If you do those without operating systems, that becomes an operating system again. So now you will become operating system in that case. So those things must be coordinated. If you don't coordinate such activities, it will be like chaotic execution. It will be like Market Street in Afghanistan, for example. Everybody is everywhere. There are no rules. So if you get early, you are done. Even in that case, there are some rules. So there is an operation. So if there is an operation and if there is somebody overseeing, controlling the operation of everything, then you say you have an operating system. There is a nice analogy for operating systems that I make. That's related to car mechanics. So repair shops, car repair shops, or other mechanic repair shops. Doesn't have to be car. So I'm going to talk about that later now. In the early days, as you asked, there were tasks such as find the code of the Germans in the Second World War. So there was only one task, one problem, one mathematical formula. That mathematical formula was to be executed. They write code for it. They program the computer, usually in hardware. They change the register by hand. Then they push start, so program counter increments, and then it executes like you do in the simulator. If the task is finished, then programmer says, okay, this is finished, then next one is executed. In the old days, computers were like that, and the coordination and operation was done by a person who was called operator. It's just like an operator in taxi station. It coordinates the activities manually. There is no automated system. But for example, in Uber system, there is a coordinating application, right? So it is automatically coordinated, who gets where, what, etc. But in taxi station, you get calls and you decide it as a person. So in the old days, it was like that, and jobs were done because there was only one computer, big computer. Jobs were done one, and then the next one, and then the next one, and the order was determined by the person who was the operator. So if you are friend of the operator, your task will be executed faster. Or if you are a professor with respect to student, the operator in the computer center will do some favor for you. So your task will be finished earlier. Okay, with torpil, etc. So after that, in the video you will watch, Fernando Corbato's video, they decided to put interactivity to programs so that program says something, you say something, program says something, you say something. So we call it as dialogue. Not a dialogue like a window, but answer and question interaction. So do you want to continue? Yes. So that kind of interaction. Please enter number 1, 2. Please enter number 2, 3. Do you want to continue? Yes. And then the result will be printed. So that's an interactive computing. Okay. So that requires immediate processing of things. You don't wait for the lunch. In the old days, you do your homework. You submit your job is executed, then your job is printed out for submitting to the professors as a homework. So you don't see the results immediately. You see the results in the printout. But they invented interactive processing. Then multiple people, if you are doing interactive processing, there is a problem because computer is expensive. If it says, please enter number 1, it waits for you. And you are smoking a cigarette, for example, somewhere else, and computer will wait, and waiting takes time. And it is also expensive because computer does nothing. You paid for the computer and the computer is doing nothing. Therefore, they decided to combine multiple people so that if one person is smoking cigarette, thinking about what to enter, other process, other person's task can be executed. So little bit this one, little bit this one, little bit this one, little bit this one, in a very fast way. Then multiple people can work simultaneously. It looks like simultaneous. It is not simultaneous, but it is like simultaneous for them, for the people. Then, as time progresses, after 1970s, multiprocessor machines, even 60s, multiprocessor machines invented. In one computer, there will be more than one processor. Multiprocessor machines are obviously can do much better because if one arithmetic logic unit is doing something, another arithmetic logic unit of another processor can do something different. So more jobs can be performed, but it has to be coordinated. Which processor gets what, etc. Any questions? So I'm going to show you my analogy here. This is the mechanic shop analogy. You have processes. How many processes we have in this computer as an operating system? Yeah, I can see three processes or three tasks to be completed. Three tasks to be completed. Task completion means fixing the car. So it is task. So in this case, it looks like two, but I said one here. There is one CPU. There is one CPU and three cars. So it's like you work on one car a little bit, then move to another car a little bit, half an hour on one car, half an hour on another car, half an hour on another car. And if the customer calls, you say, okay, I'm working on it. No problem. Or if the customer is watching from the window, they will believe that you are working on their car. No problem. But actually, you are working on three cars. So it's in a coordinated fashion. Sometimes you have dual core. So you can have multiple processors. You can have dual cores. So in that case, your performance increases. So multiple tasks can be executed at the same time with the multiple cores. Right? Sometimes I tried to find a police car who is waiting in front of a mechanic, but couldn't find that. I just found this. If you have a priority, your task is finished earlier. So between tasks, there is a priority scheduling issue. Some processes are needed to be completed faster than others because they have higher priority for certain reasons. They are network processes, they are operating system core processes, or they are communication interactive processes. And for example, an antivirus application has less priority. It's not urgent. You scan your hard drive slowly, no problem. It shouldn't slow down others. So it waits on the side. If the processors are free, then they will do it. If you have low priority. If you have high priority, they spend most of their time to fix your tasks. Fix your task. So it's a priority issue going on. There is a priority issue going on in operating systems. And there is some scheduling going on. Whose car is going to be fixed when, at what time? So which one is going to be fixed earlier? Which one is before? Which one is after? So or you can swap if you have some priority, some card, customer card, etc., or bonus card, whatever, right? So there is a scheduling thing going on. There are some tasks that are short. Some programs immediately executes and finishes. So they are short, light tasks. Some tasks are very heavy. It takes long. So between long tasks, maybe they go to lunch. Maybe they leave it because they are waiting for parts, which is input and output, waiting for parts. And they do something else. They fix another car while waiting the parts, so that they keep themselves busy. We call it as throughput and CPU utilization. If this CPU guy with T-shirt waits a whole day for the part, doing nothing because part is not arrived yet, you will fire him because he is not utilized. So you expect him to work on another task as part is coming, because part is not available yet. So input is not input and output is not finished yet. So CPU must do something else. So that must be coordinated. Do you understand? And there are other processes waiting on the line. So some processes are on the waiting line. hood is not opened yet. They are not inside the CPU. They are not in execution, but they are on the waiting list. So there is a waiting list waiting outside, parked, and those tasks must be brought into memory and then executed one after another, so that all tasks will be finished. In the old days, as I said, you put your job to queue. The queue is a mechanical queue, like papers and boxes, because they were using punch cards. Punch card, each in the punch card system, each line is one card, another card, another card, another card. So you put the box to the person who is responsible from operations, and when the time comes, when the turn is yours, they put the cards into card reader, like money counting machine. Your program is taken into computer and it is executed, and the results will be printed. That guy or girl will take the printout and put it in the output shelves, so that you will collect your shelves afternoon or next day or next week, because it's batch. You wait for your turn and you get the results. In the interactive processes, you start your application and the results are immediately displayed to people, to user. So it is interactive. You see outputs and you also respond it, and you see other outputs. Those applications are like drawing applications, text processors. Most of the things that we do today are interactive processes. However, virus checkers, print spoolers, firewalls, for example, firewall applications are not interactive application. They run at the background. They run continuously, but they run at the background. So it's not interactive. So some applications work in an interactive, non-interactive way. Batch applications are, for example, applications like send email every morning to yourself. You write an application, it sends email to yourself every morning. How do you do that? You use timer in the Unix system, etc. So you put your program on the server, checks the clock, and there is a cron mechanism. A cron mechanism checks whatever is necessary at the time when the time comes, and when the time comes, your mail is sent, for example. So that's batch processing. You submit the job, you give your job to computer, and computer executes it whenever it is necessary. So in general, you have a computer hardware at the bottom. This is top-down approach, and usually you will see this until the end of your life. On the top of computer hardware, there is an operating system. There are application programs and system applications. Then with those applications and with those system applications, many users work on the computers. Many users means many windows or many applications of the same user as well. So multiple applications are running on your computer means multiple users actually. They work like multiple users, but they are yours. So it's like same company's cars are taken to the machine shop by different people, because in the company there are multiple cars. For example, the university has like 10 cars for the rector's office. So if you take those cars to machine shop, who is the user? Gebze Technical University. I mean, same user, but multiple tasks. So each of them will be treated like different user in theory. So there are different types of operating systems. Some of them are batch operating systems. So there are sequence of jobs, one job, another job, another job, another job. It's like a factory. You do these, finish, you do next, finish, you do. So that's the old way of doing it.
Is there any?
Today, for special purposes, yes, you can do it. For embedded applications, yes, it does something, it does another thing, it does another thing. But for end user computing, no.
Can you give an example?
No, I can't give an example because I mean it's not a brand or it's not a salt for an application. For example, you want to check the irrigation of a farm, for example. You check temperature and all the sensors. You finish. Then you check rain levels. Finish. You check water something. You check security. And you go back. So it's an embedded system with Arduino, for example. So it's basically periodical thing related to periodical things to be executed. In the time sharing operating systems, there are multiple people. There are multiple tasks happening at the same time. You can have one usta, you can have many usta. So multiple CPUs is a possibility, but not necessary. For single CPU, multitasking is also possible. Multiple CPU, multiple tasking is also possible. For example, four guys can work on 10 cars. No problem. So there are distributed operating systems. Part of the tasks are implemented in here. Part of the tasks are implemented in somewhere else. It could be distant or it could be in the same building. So in the same building, for example, you can have 10 machines and tasks are shared by different machines so that the whole power can be used. Sometimes you hear the biggest computer of the world is implemented in China or United States or whatever. Those computers are distributed network computers, tightly connected in the same room or in the same building, but different computers sharing the same task through an operating system. Operating system is coordination. There are network operating systems. It's different than others. It is not for solving certain problem for specific users. It is for the connection and coordination. So different types of computers can be connected to the same network, and that is called as network operating system. It's basically for sharing information, sharing files. Such as file sharing applications, peer-to-peer applications available on the internet, like torrent or etc. That's one example of network operating system. And there is real-time operating system. Again, certain tasks Sen değil. Certain tasks are needed to be implemented in very fast way, and furthermore, not very fast, but for certain deadline. You know what deadline is? Sharp. So if you pass deadline, you are dead. So you have to finish your task before that time. One nice example is automobile engine management. At each turn of the engine, you need to compute amount of fuel, amount of air, and amount of spark, etc., to be given at the next cycle before it happens. So you have to prepare yourself and give appropriate commands to injectors, spark plugs, etc., so that engine keeps running at 3,000 revolutions per minute. So 3,000 revolutions per minute makes how many revolutions per second? 500. No, 50. 50 revolutions per second. So you have to compute your calculations. You have to finish your calculations in shorter time than 1/50th of the second, 0.02 seconds. So if you cannot, then it's not working. So real-time operating systems for robotics, robot arms, etc., in factories, etc., require real-time operating systems because due to mechanical there are deadlines, and you have to meet with those deadlines. Microsoft Windows or Linux, today's iOS, or today's operating systems, common operating systems, are not real-time operating systems. When the job finishes, depends highly on other processes loaded, and depends highly on the platform. You cannot guarantee anything. Okay. The software loaded on operating systems are in two kinds. One, specific applications installed by users or installed for users, by or for. Second, system software. System software are utilities and similar software for helping users to run their tasks. Why are you using the computer in general? Because you have to compute something. You want to compute something. You want to calculate something. You want to see something. So those are tasks. So system software helps you with tools, with certain different applications. Those are system software, to be able to give you an easier environment for your task. These are classified as follows. Any kind of software can be divided on the platform, can be divided into two. It could be an application software, it could be a system software. If it's a system software, it could be utility, or it could be operating system itself, the central guy. If it's an operating system software, it could be part of the user interface, or it could be part of the background rotating wheel. In all operating systems, you need a rotating wheel. It keeps rotating, means it goes back, checks everything, and goes top. Checks everything, goes top. So there is a loop. That loop and with certain extensions is called kernel. It's not as simple as simple loop, but actually it is a loop. Um, okay. The components of the operating system is of two kinds. Sometimes you have shell, or so in Linux, for example, you have something like that, and for the DOS, you have the following, and that's shell-based user interface. You type, the response comes. It is not a bad thing. It's okay, but it is for certain people. Usually, it is an old way of interaction, but for the power users, it can be very efficient way of interaction. Still, it is very efficient way of interaction. Graphical user interfaces are interfaces with two dimension. You see certain things and you click on things. So in graphical user interfaces, there is usually a touch screen or locating device. Locating device could be pencil or mouse or touchpad or something different, trackball, but it is two-dimensional. In future, it could be three-dimensional, maybe. User interfaces. A user interface actually does communication with you. It could be verbal as well. So generally speaking, verbal user interfaces like Apple Siri, right, will look like they are working from text-based interface, because talking is text. When you say, please make me a coffee, it's a command. So, and it will reply, yes, I am doing it. So it's another line of text. Communicative interfaces. Who knows? Can you do this to computer? Maybe. If you program correctly, if you program a correct user interface with computer vision, you can control your computer, you can input and output with hand gestures. That's possible, and we are working on it. We are doing it in the department and as projects. It can be done. So any kind of interaction with the user is called as user interface. Kernel, on the other hand, is the main loop. It has the file access operations, controller operations like controlling hard drive, controlling printers, controlling screen, etc. Controlling memory, I am going to talk about that later. Which part of the memory contains which program? That has to be coordinated. In a machine shop, in a tamirhane, okay? Multiple cars are there. Which car goes which place? Must be coordinated. Someone has to decide it. Your algorithm may be bad, but a bad algorithm is still a bad algorithm, is still an algorithm. So without decision, you cannot place the cars. And you will have scheduler and dispatcher. You will have scheduler means which is going to be executed next. So order like a reception desk, okay? And dispatcher is actually controls. Is it going to be finished in half an hour? No. So move on this one. So it's like a foreman. It's like a ustabaşı controlling the operations of everything in the shop. You have kernel in the middle. We ask people coming from other universities in master's entry exams, and we say, what is kernel? What do you know about kernel? And they say çekirdek hocam, and that's it. So the word çekirdek is only translation of the word kernel. It's not an explanation. Okay. So when I ask you to explain what the user is, what the user means, or what is the user mode in computer, the answer should not be kullanıcı modu hocam. So that's not an answer, okay? In any kind of question. Translation doesn't mean explaining. But it's a good starting point. But you have to keep talking after that. So the kernel is the program that runs all the time, and kernel actually is a good program. That means it has to be written very carefully, without errors. It should not crash. So it has to be good quality program that is very well planned, very efficiently planned, and then your operating system becomes efficient. Yeah.
Is kernel a specific thing or
kernel is a kind word, cinsism. Each operating system has kernel. That's the part of the operating system that runs all the time. Okay, and all other applications and all other parts of the program starts after kernel starts. So kernel can start others, kernel can stop others. If kernel stops, that means operating system is locked. So you have to reset the machine. So therefore, operating system must be good quality in order not to crash.
Can we give an example of kernel?
Linux kernel, Windows kernel. So it's the kernel. I mean, it's a process. It's another process. It's another like car. But that is the first one. Car example is not very well. It is the task that makes you open the shop in the morning and close the shop in the evening. So it is the task that makes you look for what is the next car. So it is the task that you do. Welcome, sir. How can I help you? So those things are actually kernel issues to be able to get the cars in and work on them. So general task is operation of the shop, the main task. So that is what we call kernel. Like iş yeri yönetmeliği kind of thing.
Is it similar to control unit?
Huh?
Is it similar?
It's similar to control unit, yes. For example, the utilities are not kernel. These are not kernel thing. Directory means user created bundle of files and other directories. Directory path means so in Windows environment, backslashes are written backwards. Slashes are directory limiters are with backslashes. In Unix, it's forward slash. In macOS, it is again forward slash. But in the old days, this was also used. Columns were also used for separating directories. So this is what we call as path. You are all familiar with paths. Let's move on. Memory manager. Who gets where? So there is CPU, and you have multiple processes, P1, P2. So two processes, one usta, which process is going to where? Must be decided, because each customer believes that he is special. It is done very interestingly in some companies. For example, in schools, in colleges, in certain brands of high school colleges makes discount for students, 40% discount, 40% course. So you believe that when you register for the high school, you believe that you are special, you are talented student, but they do it for everybody. But they don't tell others. So everybody believes that he is special. So in terms of processes, every process thinks he is special, he is the guy. He wants to work in certain places. He wants to sit the best location in the restaurant. Normally. So there is a memory manager, allocates them, but tell them that this is the best place. Everybody thinks that it is the best place. It is the necessary place for them. Don't worry about it. So everybody is happy, but they are in different places because it is impossible to put them in the same place. Is that clear? When you turn on, you see something like this. So the address 0, it is not 0, but you can believe that way. Details are not important. The program at address 0 is executed. Program counter and also. So this program starts. This is the output of the first program that you see. Then it loads something else. Go ahead. Good question. Let's give a break for 10 minutes and come back. Evdeki arkadaşlar soru sorabilirsiniz.
GNU ne oldu? GNU. Hocam Kernel'i
Unuttum. Free Software Foundation da baş harflerine baksana bir tane.
Yo, ben kendisinin ne olduğunu
Açılımını bilmiyorum. Baksana.
Hocam,
Evet.
sizin ekranınız bana gelmiyor da siz kapatıp açma gibi bir şansınız var mı acaba? Sadece sizin şeyinizi görüyorum, kameranızı görüyorum.
Ne kadar zamandır?
Dersin başından beri de diğer arkadaştan izliyorum ben.
Diğer arkadaş çalışıyor öyle mi?
Evet. Hı.
O zaman sen açıp kapayacaksın, ben değil.
Ben öyle yaptım zaten hocam. Bilgisayarı falan açıp kapadım ama düzelmedi. Hani belki siz yaparsanız düzelir diye.
Yok, nasıl yapabiliriz onu? Ben şimdi kesmeyeyim. Kayıttayım çünkü.
Tamam
o da
hocam.
değiştirmez zaten. Sen beni highlight tıklasana şeyi, paylaşılan ekranı. Veya
Nereye dediniz hocam?
Benim videomu kapat. Görüntü videomu kapat.
Tamam.
İşletim sistemi olan bir şey var.
GNU harfleriyle anlama geliyor. GNU'daki.
Ha.
Hocam kernel görev yöneticisinden kapatabilir miyiz?
Hayır. O zaman ne? Kim kimi kapatıyor? Kendi kendini.
Evet. Öyle bir şey.
Hocam şey diyebilir miyiz? İşletim sistemi işlemciyi yöneten şey.
Evet.
GNU is not Unix.
Ha?
GNU is not Unix.
Ama o açıklama değil ki. Değil tabii.
Evet.
Tamam.
Ama böyle görünüyor açıklaması.
What does GNU mean des?
GNU Loader vardı. Bir şey
Tamam da
loadluyor
GNU
da
ne?
ne load?
GNU Open Software Foundation da. Open Software Foundation neden GNU? Global. Bilmem ne yani. Onu hiç düşünmemişim ben de.
Hocam işletim sistemini hangi dilde yazıyorlar? Öyle bir dil mi?
C'de yazarlar daha çok. C'den şeye geçmesi kolay ya. Assembly'yi düşünerek yani işte register'ları şunları bunları düşünerek yazman lazım şeyi. İşletim sistemini.
Niye sen bir de yazmıyoruz?
Yazabilir.
General Public License.
Daha mı kolay?
GPL.
İlk başta assembly yazmışlar tabii daha eski zamanlarda.
Sonra da Python falan şu an daha kolay.
Yok Python yazmaz.
Yok, işte işletim sistemi değil, program falan basit
Evet.
bir şey yazar.
Evet, evet. Daha mı basit tartışılır tabii. Python'da daha basit mi? Ben pek basit yani.
Doğru olunca Python'da interpreter değil ya. İlk önce masaüstü yüklenir, masaüstü silinir üstüne bakçılar.
Python'la işletim sistemi falan yazamazsınız. Olmaz yani.
Çok yavaş mı olur hocam?
Yazamazsınız. Interpreter var. Interpreter'ı kim çalıştıracak?
Onun için ayrı
Başka bir
kernel
işletim
lazım.
sistemi oluşturalım. O interpreter çalıştırsın.
Donanımın hemen üstünde olacak. Böyle o oraya yaptı, böyle yaptı olmaz. Simülatör yapabilirsin.
Yani. Deadline neydi? Onu tam olarak
Ne?
anlayamadım da. Deadline.
Ben anlamadım.
Deadline.
Evet.
Deadline ödevleri son teslim etmeniz gereken tarih. 10 tarihten sonra teslim ederseniz zayıf alıyorsunuz. Dolayısıyla otomobilin motoru mesela dönerken 3000 devirde dönüyor diyelim.
Evet, hocam.
O dönüş tamamlanmadan ne kadar yakıt püskürteceğini hesaplayıp mikro işlemcinin arabanın beyni diyorlar ya.
Evet.
Onu hesaplayıp bir komutu göndermesi lazım enjektöre. Zamanı gelince onun şey yapması lazım. Yetiştirememesi diye bir şey söz konusu olamaz yani. Yani gecikme falan olamaz. O tip bilgisayarların real time çalışması lazım.
O kapanıyor mu?
Ne?
Yetiştiremezsin.
Yetiştiremezse
Araba
araba tekler. Olmaz yani.
Yabancı kaynaklarda da öyle görünüyor.
Ne görünüyor?
GNU is not Unix. Yani ben başka bir şey bulamadım.
Hocam Windows hangisine giriyor?
Bir dakika.
Hızlısın kardeşim.
Nasıl?
90 kilometreden.
GNU's not Unix'in şeyiymiş. Anladım. Baş harflerinin not'ının neyse.
Evet ondan bahsediyorum ben.
Sen öyle değil. Anladım. Ama G ne?
Orada GNU'dan geliyor işte hocam. GNU'nun C'sinden geliyor. GNU is not Unix. Ve sonsuzluk oluyor.
Nereden buluyoruz ya?
Recursion.
Aynen evet.
Ödebiliriz öyle.
Ama döndürülüyorsun.
Mesela ben Linux'un da bir işletim sistemi olmadığını düşünmüştüm. İşletim birimi gibi bir şeydi.
Takma isim yani. Orada bir çakallık yapmışlar. Güzel.
Evet.
Sebeplerini soruyor. Yuvarlasan nasıl olur falan. Orada sebeplerini tam açıklayamamışım. Biner'deki floating point'ler falan var ya, onlar hani lost oluyor falan ondan sonra.
Ben de
Biraz kafam karıştı. Yani sakinler
Binary'deki
bu floating point yazarken %'den öyle 2 üzeri 3 bölü 4. Onlar yazarken
Yani şu an hiçbir şey anlamadım. Onları bayağı tekrar önemli bir şey mi o konu?
Bir daha bakarsın kitaptan bir okursun.
Yani mesela 2 üzeri 3 bölü 4'ü yazarken nasıl yazıyoruz yani?
2 üzeri 3 bölü 4 değil ki o.
Normal sistem. Yani
2 üzeri 1 bölü 4.
öyle mi? Yanlış mı hatırlıyorum? Olabilir. Kitapta sormuş da question. Hiçbir şey. Yani onları yapamadım. Bayağı bir şey olmuş. Arkadaşına sordum mu? Yapamadık yani.
2 üzeri 1 bölü 4.
Nasıl yazar?
3 bölü 4 yapamaz.
3 bölü
1 bölü
8 de
4
var.
artı 1 bölü 2'den.
4 değilse.
Onun kuvvetini alacaksın.
Neden hocam? Yani 1 bölü 4 artı 1 bölü 2'ye.
Dönüşümlü olarak yapıyoruz.
Yapamaz mıyız?
Toplamaya dönüşmez ki.
Tek seferde nasıl yazacak ki?
Biz zaten toplama şeklinde yazmıyor muyuz? Yani
Evet de 2 üzeri 3 bölü 4'ü nasıl yapacaksın?
2 bir kısım sağ tarafta 2, sol tarafta 3 bölü 4'ü tamamlayacak. 3 bölü 4'te de 1 bölü 2 ile 1 bölü 4'e 1 yapmayacak.
Yazmam lazım şimdi.
Yani hocam onların üstüne çok durmaya gerek var mı diye soracağım. Onların
Bir tane
sözlerine çok
soru
kafam
sorarız.
karıştı yani.
Bir tane soru sorarız belki ama çok şey değil. Çok zor sormayız. Evet hadi bakalım geçelim. Görüyorum ya. Okay guys. So when you turn on the machine, certain instructions are executed. Then in the read-only memory of the computer, we call it ROM, read-only memory. Some people call it as firmware. Some people call it as BIOS. Some people depends on the application, depends on where you use it. So it's in the read-only memory, and read-only memory executes program. It is predetermined way of thinking that both operating system application and the program in the read-only memory had an agreement before in the factory, in the design. Read-only memory application knows that operating system will be located in certain part of the memory, which is named as master boot record of the disk drive. Master boot record of the disk drive is read, and the corresponding code is loaded to RAM and started execution. So that is what we call boot operation. It is predetermined. Locations are predetermined. So when you install an operating system, you install those locations as boot records. So boot records indicate that where your operating system is and how it should continue booting. Every time you turn on it, yes, it does. Or every time you restart. Yeah. Yes. That is another layer. That is another layer in the boot operation. It allows you to have more choices. Then it jumps to operating system. Operating system kernel starts running. It is called as bootstrapping. So same thing in the ROM, same thing in pictures. Bootloader is a program in the ROM, in the flash memory of the computer, inside the computer. It is by design. So that executes, then it loads operating system code to memory. So operating system is loaded to certain part of the memory, then it starts executing. I think it's clear enough. That's what booting process is like. Processes are like, as I said, cars. They have to be fixed. They have to be processed on. They have to be worked on, and there are many of them. Some of them are short. Some of them are long, etc. Actually, processes means program in action. So process is program in action, meaning that if the program is written on the paper, it's a computer program. No problem. It's a computer program on the paper. It's a computer program on the editor. It's a computer program on your hard drive. It's a program. But if it is running, it's a process. I won't use the word running for certain reason, because running means actually running at that time. So in action is actually a little lower than running. The process thinks it is running, but it may not be running. Just like the cars thinking that they are being fixed in the shop, but the usta is working on another car. So at that time, nobody is working on the car, but the owner thinks that my car is being fixed, my car is being serviced, no problem. It is in the shop, the hood is open, so it looks like it is being worked on, but nobody is around it, no problem. So we say it is in action. So in that case, we call that program as process rather than program. Sometimes it's called tasks, although it's slightly different. And process state indicates what is going on in the process. Where is the program counter? You are all familiar now. So you see, if I didn't teach you program counter, registers, assembly, how did you understand? How would you understand this? When I say program counter, you will just memorize it, program counter. So now you understand what program counter is. It determines where the program is in the memory. It shows the next instruction to be executed. This is my process running. So program counter is 1. Registers are the state of the process, and certain part of the memory, beginning part and end, where is the location? Okay, is important because the mechanic sometimes leaves your car. As I said, he doesn't work on, he or she, it doesn't work on your car. When he comes back, he has to remember what was the problem, what was the last thing he was doing. He has to remember. He also has to remember where was the car. So he is remembering where was the car corresponds to memory location. Where is my process in the memory? So where is my car in the shop? Second, what was the last thing I did? We should not expect them to remember everything. So what happens is they have cards in mechanical shops. You have title, probably. You have the owner, Ahmet Bey, right? And you have tasks. Silecek, değişti, yağ kondu, filtre, etc. tamamlandı. So you may stop at this point, okay? You may stop at this point and go to somewhere else. Some other car. Because a policeman came up, wants to fix its tires, fix their tires. So you have to leave this car, go to the other car. So since you are keeping what you have done as check marks, right, on the card, when you come back, you can start easily. So that is what process state is. And a data structure named as PCB, process control block, contains all the informations. It is saved when the task is not running, because CPU will be emptied. Your usta is so dumb, so unintelligent, so that he cannot remember these parameters by hand. So he has to write it and leave it somewhere. He can only understand, he can only keep track of, because registers are in the CPU, one set of process. If you are working on 3 different cars, he cannot remember. So the solution is write those contents of the registers into cards and store those cards in memory. When you switch the cars, bring those cards, restore registers with the particular car registers, then continue working on the particular car that you want. So that is how task switching is done, because the guy is very unintelligent. You should also store where the car is, because he may not remember where the car is, and he may do the same operation, the targeted operation, to different car, thinking that the license plate was the same. So you have to record where it is. So these processes, these cards needs to be administered. That's the task of that's the job of the operating system. One job is scheduling, another one is dispatching. Scheduler actually deals with new processes. You click on something, new processes started, and it is added to the queue. So it is like welcoming new cars. Dispatching means Ahmet Usta works half an hour on this, Mehmet Usta works half an hour on this, and after half an hour you say, this is enough, customer is looking at us, go to the next car. Then he switches the cars. So that is what dispatcher is. It's like a ustabaşı. Leave that for a while and work on this car. So it has to be told by the operating system. So I have certain images again. This is our scheduler. So for the new customers, for new allocations, who comes first, who comes last, who comes after who is determined. This one is dispatcher. This dispatcher controls the CPU. Actually, dispatcher is another task. O da bir Allah'ın kulu. It's another application, right? But the difference is, this is user, this is kernel. So kernel has more authority. So if kernel says stop, this guy stops, no problem. It's both of them are applications. I mean programs. It is not a hardware device. That's what I mean. It's another application. Any questions? So just like the examples are very good. So you, I think, understood. When you look at the more rigorous drawing, it says over the time passes in this axis, you work on something, you work on some process, another process, another process, another process, another process. In between, you leave the car, you leave the process, and you move to another process. But in the meantime, there is something called switch, process switching. And as I said, the usta is very dumb, unintelligent, so he cannot remember where he was. You have to write it. So that is what task switching, process switching is. It takes time because you have to write and leave the paper on the car, on the task, so that when you come back, you restore your brain. Okay, this was the thing, you remember, and you continue. That's task switching. Actually, it is done. Task list is done in the cars, because multiple people are working on your car when you leave your car in the service. So there is a checklist. They basically have a form. So different usta people fills certain checklist and they write certain things. So when next one comes, he can pick up from the last part. They don't talk to each other personally. They communicate through the paper. That means when you have dual core operating system, if your process is running on core A and due to multitasking, after switching to process B or C, when you come back, you may be working on core B instead of core A. So you cannot be sure which core you are working on when next time comes. So your car can be fixed by different ustas in an exchangeable manner, in a time shared manner. Okay, there are interesting facts. One, if you are cleaning the ground, what do you say? Everybody out. Nobody should come because the ground is wet. So you are doing something yourself, but you want other processes wait, because that area is now only for you. No other usta should enter. You are cleaning or dropping something. So for those kind of things, or you are painting someplace, you are painting the car. Let's talk about cars. You are painting the car and you tell others that don't touch the car because it is painted, or it has some glue, so it should wait for half an hour for glue to fix. In that case, others don't touch. So that is what semaphore is. Programs can share information, critical information, and semaphore is used to eliminate simultaneous access to certain parts of the memory, so that conflicts should not be conflicts should be eliminated. How many people can go into one toilet at a time? One, normally. Probably. So toilet is a critical region. If you enter toilet, no other person can enter. So you have to make a mutual exclusion. You have to make a mutual exclusion so that as you enter, you lock. When you lock, others cannot try it. When you exit, you unlock. Okay, as a program. But if you enter and if you die inside, what happens? Die means crash. No one can enter. And they realize that after a couple of days, the bad smell comes out because there is a dead person in the toilet, right? So they have to reboot the machine so that all the doors will be open again. So it is a problem. Therefore, kernel must watch all these resources so that if there is a violation, the violation should be eliminated with a master key. Kernel can see the toilet. And actually, kernel is set to work like a janitor. Janitor means temizlikçi bayan veya erkek. They have keys to all rooms. Maybe they have more keys than rector. So it is not the authority they have, but they have access to everywhere. So they can look after a lot of things. So that is done by the operating system. Mutual exclusion and critical regions. These topics will be studied in third year in operating systems course. But as I said, for example, in some applications, toilets are locked. How do you get into toilet? You go to the office, you get the key. That's the procedure. You get the key, you go to toilet, and you lock from inside. So if the second person wants to go to toilet, uses the same procedure, goes to office, key is not there. If key is not there, he keeps waiting until you bring the key back. So that's exactly a procedure that is used in operating systems, key lock procedure. Sometimes you have multiple resources, such as multiple toilets. So two keys are available. So you take one key and go. Another person gets the second key and go. Third person comes, no key. So third person waits. These kind of lock key issues also create problems in certain places. One of them is the deadlock. You take the key to go to bathroom, but the other guy who was in the bathroom has to, but he needs a toilet paper to be able to go out. I mean, he is stranded in the toilet because there is no paper or there is no water, whatever. So he waits. He needs help, but the helping person also wants to go to toilet, and in order to bring help, he has to go into toilet. But who needs help? The guy in the toilet. So they wait for each other. One guy is expecting toilet paper, another guy is expecting the key. So they will wait forever. So this is called as deadlock. It is due to competition of non-shareable resources, competition for non-shareable resources by multiple parties, multiple programs. For example, you need disk drive, and hard screen, graphics card to do something. You get the disk drive, but hard graphics card is taken by the other guy. Other guy is also doing the same. He has the graphics card, but not disk drive. You have the disk drive, he has the hard drive, but both of you needs two resources in order to finish. You cannot finish because you don't have graphics card. He cannot finish because he doesn't have hard drive. So what's going to happen? There are two solutions. One, you need to make sure that you don't go into that situation without obtaining permission for both resources. So without toilet paper, don't go to toilet. You have that rule in the system. That cannot happen. The second, supervision system checks whether there is an extensive waiting. If there is a waiting, they say they kill the guy. Actually, they kill the guy, and if the guy is killed, who was waiting in the toilet, that means it is cleared, so system can continue. You can ask him to go again by restarting the application. Beklenmeyen bir hata oluştu, lütfen sonra tekrar deneyiniz gibi bir şey oluyor yani. So a train example. Train example is as follows. This train, in order to go, this is train A, this is train B. Train A cannot go because train B is blocking. Train B cannot go because train A is blocking. So what's going to happen? This is called as deadlock. Another example, another famous example is in United States. These are roads. It says do not block intersection on the ground, or sometimes there are traffic signs. Do not block intersection. When there are lights here, when lights turn to green, turn to red, you should not proceed to the middle of the street because other parts cannot move. The problem is exacerbated when you have Manhattan style grid. This cannot go because traffic is jumped here. This cannot go, traffic is jumped here. So if you block intersection in one of the corners, the traffic in the whole area cannot move. So you cannot move because of yourself, actually. That can happen. Another example is, çözülmüyor. In the old days in Manhattan, it is said that police were called and they were manually pull the cars to side in order to free the street. That's very interesting issue. It also happens in roundabouts. In Turkey, there is a yield sign in roundabouts. People don't give way. They just go into the roundabouts. So if everybody goes into roundabouts, it doesn't rotate. Traffic cannot rotate. Everybody wants to enter. Nobody can exit. If nobody can exit, going into roundabout has no meaning. It is useless. That's why you have give way sign, but our drivers don't take that into account. So the priority is those who are in roundabouts, döner kavşak, rather than priority is in the guys who are already rotating. So you should wait. If you don't wait, you cannot go out. She gets the oil to start cooking. So she has the oil. Adam gets the pan. Amy waits for Adam. Adam waits for Amy. It cannot be finished. So this is what we call deadlock. In order to prevent deadlock, you need to have rules. Those rules should prevent deadlock, as in rotating traffic. Those rules say that you need to obtain all the requirements before starting. So if Amy thinks that she has to have oil and pan, then go. Otherwise, release. Otherwise, leave it. Because if you cannot obtain pan, it doesn't help. So release the oil too, so that if anybody wants, Adam or somebody else can finish the task, releases also oil, then you can start again. So those are the rules to prevent deadlocks. Lastly, operating system deals with security issues, security and privacy. In the old days, when operating systems first invented, everybody was students or people who are working in the same company. So if more than one application was running, they knew other applications. They were their friends. So nobody touched each other. So there were no locks in the houses all days. But after you introduce foreigners to the institution or foreigners to the country, robberies were more increased. So you need locks. You started to use locks. Similarly, in the operating systems, different applications work differently. They are written by bad people sometimes semi-bad people. They are working, but they want to get more information. So you need to protect different users from each other. You need to prevent people from seeing each other's files. In the old days, no problem. My stuff is yours, like an old Turkish village shop. You can sell items from the next shop. You can keep track and you can give the money to your friend's shop when he comes back. No problem. But now you have to make sure that security is available. Therefore, things like password, logging with passwords, password authentication, password management, those are done by the operating systems. Also, encryption of data for communication can be implemented by operating system so that user data is sometimes it is not only bad. You don't want your files to be seen by others. It's not because they are going to do something bad. You just don't want to see. You just don't want to see it. Private photographs, for example. So it has to be protected. So internal attacks also interesting. Sometimes there are attacks from outside of the computer, from the network. Sometimes attacks from the inside. So virus programs, for example, attacks your data. They want to encrypt your data and ask for money. Ask for money. In these months in Turkey and in the world, attackers ask for money depending on how much you earn in the company. They ask a proper amount of money and they get it to release your files because they encrypt your files and you cannot get your files back. For a small company, they ask like 10,000 liras and the company pays 10,000 liras in Bitcoin and their files are back. So these are security issues that need to be addressed by operating system. Okay, so far so good. Any questions? I'm going to talk about high level and C programming language. Now, low level language means simple, closer to machine. So as you get closer to machine, we call it as low level languages. So machine code is the lowest level. Assembly language is the level above. high-level languages are more like visual programming languages. You introduce blocks. So it is high-level programming language, flowchart, visual programming. In between, you have Java, Python, C++, C#, Pascal, Ada, PL1, APL, different computer languages. There are hundreds of different computer languages. Lua, for example. Most basic, most are compilers. Some of them are interpreted languages. Interpreted languages, as we discussed last time, they are executed one line by one line by the system, or by the operating system. We call it by the application of the operating system that we call interpreter. Compiled languages are converted to machine code by a computer program, which is called compiler. Compiler compiles high-level language code and turns it into machine language. Interpreter understands interpreted code, executes it, rather than generating machine correspondence, machine equivalent. So one of them is translator, one of them is doer. C is a language that first suggested by Brian Kernel and Dennis Ritchie. Kernel and Ritchie in early 1970s, 1970 actually, as they first, I wouldn't say invent, but as they first wrote Unix operating system. So Unix operating system was written in C. C is actually one step away from assembly programming language. It's a big step, but it's, I think, the closest relative. So it's a common language used by a lot of developers throughout the world, and it is the father of many other languages like Java, C++, C#, etc. In the older days, there was a computer language called Fortran. Fortran is named after formula translation. It's another computer language. The idea is people were using computers for calculations, for engineering mostly, because it was expensive. Nobody was playing games. Therefore, the task was mostly formulas, calculating wages, calculating building calculations, etc. So there were algorithms to add these. There were formulas for computations. Therefore, one guy said, we are going to translate these formulas to assembly language, to machine equivalent. So that's why the name of the language called Formula Translator and Fortran. That's why they call it Fortran. And Fortran is probably one of the earliest languages, earlier than C, to be used in computers to generate machine code from something more understandable by humans, which are formulas. From algorithms to machine code. C is therefore industry standard So everybody should, if you are pretending to be a computer engineer, you have to be able to write C efficiently. It is so simple. If something is very simple, such as an X, it is very easy to learn it, but it is difficult to be a master. So you can learn it. C has very few keywords. Syntax is simple. It's not complicated. So once you learn C here, you say, I know C. But are you a good C programmer? It depends. It depends how you master with the language. But the minimum requirement is satisfied. You know how to write in C, and then it is a basis for C++. So those languages are not that much different. Also, the programming language of Arduino, they're all same family. C programming language book is by Kernel and Ritchie. That's the book written by the inventors of the C programming language. That's available. I suggest you to look at it and check it and try to read it. It is not difficult. It's a reference book, so it doesn't teach you. We are going to teach you. We are going to discuss things. You can learn also from there, but it is not a lecture book. It's not a class course book. On the other hand, most C programming courses in the world follow that book as a reference. So that is the core. That's the original C language. I think we can stop for now because I am going to go into algorithms and C equivalents next week. Thanks for coming. You will have a homework for about 10 days. I am going to give your homework tonight. Okay? It's Arduino.